Hello everybody, Namaskar. So in the previous lecture I have discussed the steam ejector refrigeration system. So in that system the main specialty is that we have used the water as a working fluid, and for the water, due to the use of water, the system pressure, that is the negative pressure. So that means the evaporator pressure is also negative pressure, condenser pressure is also negative pressure. So and that system has been developed in many years ago, and that is widely used in the industrial application. But after that, nowadays when we are talking about the use of the renewable energy, then we can also use some other refrigerant for the ejector refrigeration system. So when we will use the other refrigerant for the ejector refrigeration system, so for this case pressure is the positive pressures. So that's why that cycle has been modified and to make a modern type of ejector refrigeration cycle. So the modern ejector refrigeration cycle that we will discuss in this lecture, and with the emergence of the renewable energy application, the importance of this cycle has been increased very fast nowadays. Okay, and this has become a very promising cycle for the renewable energy application. Okay, so what I have already told, that the ejector refrigeration system is basically the thermally activated technologies, or thermal energy is used in case of the mechanical energy for the vapor compression cycle. So instead of the compressor, we are using the ejector to increase the vapor pressure from the evaporator pressure to the condenser pressure. Okay, so the ejector refrigeration cycle, which are widely used nowadays for the renewable energy application. Okay, so which is very promising cycle for the renewable application. So this cycle can be represented by this way. So as you can see that this cycle is basically consist of the different components. So the vapor evaporator and the condenser and the expansion valve, these are the same as the simple vapor compression system. And apart from this, or the instead of the compressor in a vapor compression cycle, here we are using the ejector, pump and the generator. So basically the combination of ejector, pump and generator, that is doing the same work what the compressor does. Okay. So for this case, you can see that after the condenser, if we assume that the condenser outlet condition is the saturated liquid, so at 0.5. So at 0.5 we have to divide into two parts. The saturated liquid will be divided into two parts. One part is going to the evaporator through a expansion valve. So that means the 5 to 6, this is the expansion process in a expansion valve, and that is in between the expansion from the condenser pressure to the evaporator pressure. And then 0.6 which is in a two-phase zone, and that is going to the evaporator, and in evaporator that is absorbed heat from the heat source, and this is converted to the vapor at 0.3. So for the theoretical analysis, we will assume this as a saturated vapor at 0.3. Okay, and this flow rate, let's say the m dot E. So m dot E is the mass flow rate to the evaporator, and that is also flow rate of the secondary fluid for the ejector. Okay, and in the other side you can see that the mass flow rate m dot G, this is the mass flow rate to the generator. Okay, so that mass flow rate is going to the pump, and that is pump, and that pressure is increased from the condenser pressure to the generator pressure, and from the state point 5 to state point 1, then that is going to a generator, which that fluid will absorb heat from the generator, and that is converted to a vapor, and that may be the superheated vapor or maybe the saturated vapor at 0.2. So this 0.2 for the theoretical analysis we will assume as a saturated vapor at 0.2. Then these two at 0.2, and that mass flow rate is m dot G. So this is basically the primary fluid for the ejector. Okay, so that means for the ejector, the primary fluid flow rate, which is the state point 2, that is the m dot g, and for the secondary fluid flow rate, which is the state point 3, and mass flow it is m dot e, and after the ejector we are getting the state point 4, so that the ejector is used to compress the vapor from point 3 to point 4, and basically for which case we are using the thermal energy which is gained through the generator to increase this pressure. Okay, so that means state point 4, the total pressure, that is m dot E plus m dot g, and that is going to the condenser, and that is condenser. We can ideally get the saturated liquid outlet at 0.5. So by this way the cycle will work. So what I have already discussed, that the condenser, evaporator and throttle valve, these are basically the same devices which are used in the vapor compression cycle, and instead of the vapor compressor in a vapor compression cycle, we are basically using the combination of this ejector, generator and pump. So combination of ejector, generator, pump, that is basically also called the thermal compressor, because the thermal energy used to, instead of compressor we are using this thermal compressor, which is used to compress the vapor from the evaporator pressure to the condenser pressure. Okay, so for the temperature entropy diagram and the pressure enthalpy diagram, both are listed in this slide. So we can see the different processes of the cycle. So there are basically 3 temperature or 3 pressure. So one is the evaporator pressure PE, and that corresponding constant temperature line for the evaporator temperature. Another is the condenser temperature or condenser pressure PC. Another is your generator temperature or generator pressure is the PG. So basically the outlet in the evaporator 6 to 3, this is the evaporation process or the heat addition process. So this 3 is the secondary fluid inlet for the ejector, and at 0.5 what I have already discussed, that the 0.5 we can take as a saturated liquid, and 0.5 both the fluid are divided. One part is going to the evaporator, so which mass flow it is m dot E. So 5 to 6 is the expansion process, isenthalpic expansion process, and 6 to 3 is the isobaric heat addition process. And another side, that 5 to 6 is the adiabatic compressor process in a pump, and then 1 to 2 is again the isobaric heat addition process in a generator. So 0.2, this is the inlet conditions of the primary nozzle, and 0.3, this is the inlet condition of the secondary nozzle. Then 2 to 7S, this is the isentropic expansion through the primary nozzle, and 2 to 7, this is the isentropic actual expansion in a primary nozzle. So the 7 is the actual output of the primary nozzle, and similarly the 3 to 8S, this is the isentropic expansion in a secondary nozzle, and 3 to 8, this is the actual expansion in a secondary nozzle. So this M is represent the mixing chamber. So PM, that pressure is the pressure of the mixing chamber. So then the 7 and 8 both are mixing together, and after the mixing we are getting the state point M. Then M to 4, this is the process in the diffuser, so pressurize in the diffuser. So this pressurize will be up to the condenser pressure at 0.4. Then 4 to 5 is again the condensation process, that is the heat rejection process, constant pressure heat rejection process in a condenser. Okay, so to do the theoretical analysis for this cycle, ejector depreciation cycle, we have to make some assumptions, and I have already discussed many things related to the assumptions, like that the evaporator outlet and condenser outlet both are saturated. Then the vapor stream from the separator is saturated vapor, and liquid steam from the separator is the saturated liquid, then flow across the expansion valve, and throttle valve is the isenthalpic, and both the motive and steam section are reach the same pressure, that means that is the mixing pressure. So at the inlet of the constant pressure mixing section, then there is no mixing in between the SME before the inlet of the mixing section. Similarly, the expansion efficiencies of the motive nozzle and suction steam are given constant, and diffuser of the ejector also have the given efficiency, and kinetic energy of the refrigerant at inlet of the ejector and also the outlet of the ejector, that is negligible. Okay, so for the theoretical analysis, I have in the previous lecture also I have already discussed these issues. Okay, so for this case we are also taking care of the expansion of the secondary stream also. Okay, so for the primary nozzle, these are the equations which I have already discussed for the ejector modeling. So first of all, we have to get what is the enthalpy after the isenthalpic expansion, and then you have to use the nozzle efficiency to get the enthalpy after actual expansion to the primary nozzle at 0.7, and then this third equation we can use to calculate the velocity after the nozzle after the expansion in the primary nozzle. Then for the secondary nozzle also we can do the similar calculation, that H8S, that is represent the enthalpy after the isentropic process in the secondary nozzle, and then we can use the isentropic efficiency of the secondary nozzle to get the actual enthalpy outlet of the secondary nozzle, and then we can use this last equation to calculate the velocity after the secondary nozzle. Okay, so in this case you can see that the 0.5 and 5 is weight saturated, and 3 and that 0.2 and 3. Okay, 2 and 3, that means the outlet of the generator and outlet of the evaporator both at the dry saturated condition. Okay, so intermediate efficiency for this case also you can retain as a m dot E by m dot G, because m dot E is the flow rate of the secondary stream and m dot G is the flow rate of the primary stream. Okay, then we have to use for the mixing section. So for this case we can again we can use the constant pressure process. So that means we can use the first equation as a momentum equation. So C7 plus, so for this C7, this is the inlet velocity of the secondary primary fluid in the mixing section, and C8, this is the inlet velocity of the secondary fluid at the inlet of the mixing section. And mu, if that is the intermittent ratio, so C7 plus mu C8, that is equal to 1 plus mu into Cm. So Cm is the velocity after the mixing. So then we can use the energy balance, H2 plus mu H3 plus 1 plus mu into Hm plus Cm square by 2. So these two equation can be used to calculate the outlet velocity after mixing Cm and the outlet enthalpy after mixing Hm. Then we can use the mix flow to the diffuser. So for this case again we can use the first equation to calculate the enthalpy after the diffuser. Then we can use this second equation, diffuser efficiency, to calculate the enthalpy after the isentropic compression process in the diffuser. Then the H4S and SM that is equal to S4S. So this enthalpy and entropy at this point, that will give the pressure of the condenser. Okay, so for this analysis I have already neglected the shock in the mixing section. Okay. So Although if you use the shock for the calculation and if you do not use the shock, then if you see the ultimate result, so for that case the variation is not so high, because if you consider the shock, then you will see that the pressure is due to the shock, and then if you, so due to that shock your kinetic energy will already reduce. But when we are calculating, we are using the diffuser calculation, we are doing the diffuser calculation, for that case also we are basically using the kinetic energy from the conversion of the pressure energy. So that's why the overall if you see the overall scenario, then both cases ultimately the outlet condition will not so differ. Okay. So for this case, that for given generator temperature, condenser temperature and the evaporator temperature, entrainment ratio is set such that the exit pressure should be equal to the condenser pressure corresponding to the condenser temperature. So all the steps which I have already shown to calculate how the condenser pressure. Now in case the condenser pressure is given and the entrainment ratio is not given, so for that case either we have to do some iteration, so that if you assume some value of entrainment ratio and ultimately you have to match what is the values of PC we are getting from this calculation, that PC should be the saturation pressure corresponding to the condenser temperature. Okay, so that means you have to iterate the mu by this way, that the PC should be equal to the saturation pressure at the corresponding condenser temperature. Okay, so some cases, if the two temperature, generator temperature, evaporator temperature and entrainment ratio is given, so for that case we can calculate what will be the condenser temperature or condenser pressure, and if the condenser temperature, evaporator temperature and generator temperature, all the temperatures are given, for that case the entrainment ratio that you have to iterate. Okay, so then ultimately your heat rejection to the condenser can be written by using this equation m dot g plus m dot e into H4 minus H5. Then the pump to the power input to the pump, that can be written by using this equation, where the small v5 that is representing the specific volume at 0.5 and Pg minus Pc divided by the isentropic efficiency of the pump into the mass flow rate m dot g. So the expansion device H5 is equal to H6, then the refrigeration effect, this is the T into H3 minus H6. So the heat supply to the generator, that is m dot g into H2 minus H1. So your COP of this system, that can be written as the refrigeration effect QE divided by the generator heat input plus the pump work. So that means the m dot E into H3 minus H6 by m dot G into H2 minus H1 plus the pump work WP. Now in general the pump work, that is very negligible as compared to the QG heat input to the generator. So that's why if you neglect the pump work, so the COP can be written as m dot E into H3 minus H6 by the m dot G into H2 minus H1. So as you know that the mu is equal to m dot E by m dot G, so this also can be written as mu into H3 minus H6 by H2 minus H1. Okay, so by calculating the enthalpy of all the points, you can ultimately calculate what is the cooling capacity and what is the COP of the system. Okay, so for the calculation procedure in case of the ejector refrigeration system, so I have already pointed out the two type of cases may be possible. One case is that you have a evaporator temperature, generator temperature and the entrainment ratio mu. Okay, if three parameters are given. Okay, so for this case we have to calculate the performance and the condenser temperature or condenser pressure and also the performance of the cycle, like the cooling capacity COP of the cycle. And second case, instead of giving mu is not given. Okay. So, for this case the evaporator temperature, generator temperature and condenser temperature, these three temperatures are given and efficiencies are given. So, for this case you have to calculate what is the entrainment ratio and what are the other performance parameter. Okay. So, these two type of problem can be possible in case of ejector application system. Okay. So, there may be another combinations, there may be also another combinations for the any problems, but I want to consider these two specific combinations. So, so that we can easily demonstrate the how the calculation can be possible in case of vapor ejector application system. So, for these both the cases we can do some assumptions and similar assumptions. Okay. So, apart from the many assumptions already I have listed or I have discussed in this lecture. Okay. So, just I want to mention some important assumptions for these two cases. So, first assumption is the no shock. Okay. So, let us say that, so what are the discussion are given in this slide. Okay. So, all the calculation procedure, all the steps for the calculation, that is based on these three important assumptions. Okay. So, one is the no shock. Okay. There is no shock and second is the constant pressure mixing. Okay. So, velocity, the pressure change during the mixing process, that has been neglected. So, that means the momentum equation, that is only based on the velocity term. Okay. And the last one is the neglecting the suction pressure drop. Okay. So, I have already discussed in the previous slides that there is a expansion for the secondary nozzle also. Okay. So, that means the secondary nozzle inlet condition is 3, outlet condition is 8, which I have decided, and at point 8 outlet condition we have also calculated what is the velocity. We can also calculate what is the velocity after the secondary nozzle. Okay. So, that means there is a pressure drop or there is a pressure difference what we have seen in between the evaporator pressure and the mixing chamber pressure. Okay. But let us say for example, for the simplicity of the calculation, the evaporator pressure or mixing chamber pressure, that is equal to the evaporator pressure. That means the pressure drop for the secondary fluid, that is negligible. Okay. That if you neglect. So, if there is no pressure drop, that means the C8, okay, which previously I have discussed in the previous slide, C8, that means the outlet, the secondary flow outlet from the secondary nozzle, that velocity is equal to 0. Okay. So, C8 is 0. So, based on these three main assumptions, for these two type of cases, how we can solve or what will be the calculation procedure or what will be the steps. Okay. So, you can see that for these are the some of the important calculation step which I have discussed in the previous slides also. So, like that the P2 and state point 2 and state point 3 both are the saturated vapor. Okay. One is the inlet of the primary nozzle, another is the inlet of the secondary nozzle. So, for all the cases that both are saturated conditions, so we can get all the properties from the table. Okay. So, then the 2 dash, S2 dash and S3 dash, this is from the primary nozzle. Okay. So, that means the for the outlet condition of the primary nozzle can be written by this way. So, these are the some terminology difference with respect to the previous slides. So, here basically the 2 dash that is C3 dash, these are basically the outlet condition of the primary nozzle. Okay. So, then the after the mixing the condition, let us say M. So, that the Cm, Hm and Sm, this is the condition after the mixing. And then also we can get the other properties, that means the in case of diffuser equations we have to use to get the after diffuser conditions, and then the expansion process, the constant enthalpy process you have to use. So these are the some the governing equations. So that means for the performance parameter, cooling effect, and the heat input to the generator and the COP of the system. So in case of for the case 1 where the mu is given apart from the evaporator temperature, generator temperature. So for this case we can use the step by step equation to calculate what is the evaporator pressure, which I have already discussed in the previous slides. So ultimately we can get the condenser pressure and what is the steps we have to make. So that means we have to do first the primary ejector calculation, then mixing chamber calculation, then diffuser section calculation to get the outlet pressure of the diffuser, that means which is the basically the pressure of the condenser. Okay, and in the second case, for this case what we can do that before the calculation for the ejector we can assume some mu, value of mu, then we can get we can calculate what is the outlet condition of the diffuser. So then we can either we can change the mu. Okay, so then that outlet conditions, that should be outlet pressure, that should be equal to the condenser pressure, that condition should be satisfied. So sometime we can to get one thing we can also another option is that we can assume mu and then what is the outlet enthalpy we are getting after the diffuser and what is the actual enthalpy inlet for the condenser. So if you want to match this, so basically the one enthalpies at the outlet of the diffuser that we can get by step calculation. So that means in first nozzle, then mixing section, then diffuser, then we will get one enthalpy value after the diffuser. And another thing is that this enthalpy we can match with the overall energy balance of the ejector. So that means the H2 plus mu H3, that should be equal to 1 plus mu into H4. So this enthalpy and enthalpy after the diffuser, both enthalpy should be matched. Okay, so you have to choose or you have to iterate the mu by this way that the two enthalpy that will match. Okay, so either we can match the evaporator that condenser pressure or we can match the outlet enthalpy H4. Okay. So by any way we have to match those to iterate the value of mu in case of for the case 2. Thank you.